Hello, this is a response video to Veritasium's video titled The SAT Problem Everyone Got Wrong. And in 1982, there was an SAT test, and one of the questions was, if you have two circles, and circle A has a radius 1/3 that of circle B, as circle A rolls around B, at the end of how many revolutions of circle A will the center of circle A reach its starting point? Or to word it a slightly different way, what it's saying is, if you have two circles and circle A has a radius 1/3 that of circle B, producing a 3-to-1 ratio, how many times will circle A rotate or revolve as it rolls around the circumference of circle B one time back to its starting position? So some people are saying that the answer is 1, some people are saying the answer is 3, some people are saying the answer is 4. In 1982, there were a few students who said the correct answer was 4. So let's kind of just go through those one at a time and look at why people are saying it's that way. The people who are saying that the answer is 1 are saying so because in astronomy, there's a specialized definition for the word revolution, which is when an object goes around another object in a curved path in an orbit. So that one orbit around is a revolution. So I would say that the answer is not 1 because there's nothing in the original SAT question to indicate we should be using specialized definitions. So before we go any farther, let's define what a revolution, the standard definition for a revolution is. Standard definition for the word revolution is, when we're talking about circles, is for a circle to rotate 360 degrees one time around its own center, around its center. So if we rotate this 90 degrees, 180 degrees, 270 degrees, 360 degrees, that's one revolution, okay? So the reason that some people are saying the answer is 3 is because if we look at just how many revolutions occur based on degrees of rotation, we have 360, 90, 180, 270. So if we rotate this, right here, we have our first 360 degree revolution. Right here, we have our second 360 degree rotation. And when we come back to start, we have our third 360 degree rotation. Now, the reason some people are saying the answer is 4 is if we observe that A is upright, we roll it to the top of B, where it appears upright again. And they're saying that's one full revolution. We roll it some more to this position, and they're saying that's the second full revolution. We roll it to this position, and they're saying that's a third full revolution. And we roll it to this position, and they're saying that's a fourth full revolution. Now, to explain why that's happening, we have to understand something about viewing things from an external frame of reference. So what an external frame of reference is, it's just your point of view. It's where you're looking at things from. So from our point of view, we see let's flip this around so we can actually see the degrees of rotation. We see A rotate 90, 180, 270 degrees. Okay, so that's 3/4 of a turn. But from our point of view, we see the circle change direction by 90 degrees. So that 270 degrees of rotation of A plus our observed 90 degree change of direction make it look like A has rotated one full turn, when in fact it's only rotated 3/4 of a turn. It's not until here that we get our full 360 degree rotation. So while it looks like, let's just take a look at this. While it looks like A is rotating 4 times, 1, 2, 3, 4, from our external frame of reference, from our point of view, because of it's happening because of we're viewing the 4 90-degree changes of direction. Okay, so if we remove that reference frame by leaving the centers of circle A and circle B stationary, and we just roll them against each other, and we ask how many times will A appear upright, we see that it's 1, 2, 3. And that happens because of the 3-to-1 ratio. Another way to sort of demonstrate what I'm talking about is if we roll A to the top, where it appears like it's done a full revolution, okay? If we remove from the observed change in direction from our perspective by counterspinning A and B together so that A is in its original position, we can see that A is not upright. And it should be if it's done a full 360-degree revolution. I'll show you what I mean. This arrow is pointing, you'll notice this arrow is pointing at the center of B. So if we roll this around until that arrow is again pointing at the center of B, and then we counterspin A and B together so that A is in its original starting position, we see that A is upright because it actually did rotate 360 degrees. So to kind of further demonstrate what I'm talking about, let's sort of look at a different question. Let's reframe the question, okay? Let's pretend that circle A here is a planet, and on that planet we have our guy Bob. And in the center of circle B is the sun. So the question we're going to ask is, how many times does Bob see high noon compared to how many times do we see Bob's planet rotate? Okay, so here's Bob. He says, I'm ready to roll. So let's roll it up to the top. And from our perspective, it looks like, from our external reference frame, it looks like Bob's planet has rotated 1 full time. But Bob here says, no, it hasn't fully rotated. For me, it's morning time. So we rotate it a little bit more. And it is at this point that Bob says, yes, that's 1 full revolution for me. It's high noon. So then we rotate it to the second position, where from our external reference frame, it looks like Bob's planet has rotated twice. But Bob says, no, it hasn't fully rotated twice. For me, it's midnight. So we rotate it a little bit more. And at this point, Bob says, yes, that's 2 full revolutions for me. This is 2 high noons for me. So we rotate it to the third position, where from our external reference frame, it looks like it's done 3 full rotations. But Bob says, no, it hasn't done 3 full rotations. For me, it's evening time. So we roll a little bit more. And it is at this point where Bob says, yeah, that's high noon again. That's the 3rd high noon. That's the 3rd full revolution. So what's happening here is, because circle A has a radius 1/3 that of circle B, we have a 3-to-1 ratio. And because of that 3-to-1 ratio, Bob's planet only has 3 days, not 4. So Bob sees 3 high noons, not 4. So the reason for that, okay, is because if you have a 3-to-1 ratio, it's physically impossible for one of those circles with a 3-to-1 ratio to produce a 4-to-1 outcome and physically revolve 4 times. So anyway, my answer to this question is 3. Because when I look at the SAT question, I don't see anything in it that indicates we should be using special definitions for the word revolution, as in an orbit. And I don't see anything in it that indicates we should be considering external frames of reference. When I look at the SAT question, what I see is a simple question that's asking, if you have two circles that have a 3-to-1 ratio, how many times does the smaller circle revolve or rotate as it rolls around the bigger circle and one time? And the answer to that is 3 times. So I hope that explains things. I hope that helps. I hope everybody has a wonderful day. Take it easy.